Hi, students. I think we were left with only one session last time to complete our biostatistics course. Therefore, this slide is prepared to complete the portion that we couldn't be able to cover because of coronavirus. If you remember, we have been discussing about the multiple linear regression, and we have seen different features of multiple linear regression. In order to refresh your memories, before we proceed to the exercises, you have to remember what the objective of multiple linear regression. And as we have already discussed, it is used to examine the effect of one or more independent variables on one quantitative outcome variable. Therefore, it answers a research question that is interested in addressing factors affecting a particular quantitative outcome variable. Therefore, you have to keep this in mind. Secondly, we have also said multiple linear regression provides two important information. One is it gives us individual contribution of independent variables to affect or to alter the outcome variable of our interest, and secondly, it gives a synergetic effect or the combined effect of independent variables on a single outcome quantitative variable. Therefore, always when we do certain analysis, we have to be able to know what objective we are addressing in this regard. Next is the assumptions. Always when we do certain analysis, we have to make sure that the assumption, a particular model that we are using requires. In multiple linear regression, first we have to make sure that the data is normally distributed, and the type of relationship we see must be linear and should not be a kind of relationship which could be parabolic, which is not addressed by multiple linear regression. Third, the variability across the distribution of variables must be constant, and thirdly, the data point or observations must be independent of one another. We have to make sure that these four assumptions are satisfied. Keeping this in mind, now we do one exercise, exercise 432, which you have already received the data. And for some of you, we have already tried this in class as well. The exercise is about the study where a hospital manager was interested to see factors affecting admission rate of the patients to the hospital. He wanted to learn what are the factors affecting admission rate to the hospital that he serves as administrator. Therefore, he suspects two variables as determinant factors of admission rate. One is the wealth index. Probably, if the hospital is very expensive, it's only wealthy people are more likely to be to get service and to get admitted to the hospital, and poor people may shy away because they cannot afford. Therefore, wealth index is one factor that he suspects. The other one is availability of other health facilities in the catchment area of the hospital. For example, if there are many other health facilities, probably people may have another chance to go to the other health facilities, and that can reduce admission rate to the hospital. Or otherwise, availability of other hospitals may refer patients to the hospital if the hospital provides advanced services, and that will increase the admission rate of the hospital. And therefore, he is interested to see the effect of these two important independent variables on admission rate. So based on this assumption, intention, then we answer three questions. Test the hypothesis, HO that beta 1, beta 2 is equal to 0 at alpha of 0.05. Therefore, HO says that the two independent variables never predict or are not related to the patient admission rate. So we test this hypothesis. Second, obtain the regression equation. Once we have run the test, then we get the inputs from the output, and then we can write an regression equation very easily, and then calculate the confidence in 95% confidence interval for population coefficients. So that's also directly picked from the output of the SPSS. Therefore, in order to answer these three questions, first, you need to enter the data as we have discussed in the class. You can enter the data very easily into your computer and then run this analysis. As you can see, the table contains four variables. One is the identification of the hospitals, the community. Second one is admission rate, which is a dependent variable. Third one is availability of other health facilities in the catchment area of the hospital, which is one of the independent variables that affects the admission rate. And the second one is the Wells index, or index of indigence, which is likely to affect. Therefore, you have to put these four variables into your SPSS first before we begin to answer the question. Once you have done that, then we can run the test. To run the test, you have the steps already in your slide, how to go about step 1, step 2, step 3, step 4, and step 5. I think you can directly read this from your slide, and I don't need to go into that. You follow exactly this step to run the multiple linear regression. So once you have done, we have gone through the steps, then the SPSS will give you several outputs, one of which is the table of model summary. And a table of model summary is very useful in order to make sure that there is a fitness between the data and the model that we use. And we use R-square to decide or to know whether the model is fit. So R-square must be greater than 0.1 or at least 10%. And if that is satisfied, then we can conclude that the model is fit. Therefore, we continue with reading the model. Therefore, in this case, as you can see from this output, the model fitness R-square is 0.668, which is 66.8. So it is much greater than 0.1, and therefore the model is fit. Another information that model summary provide is then the amount of variance in the outcome variable explained by the independent variables. This is, you multiply this by 100, and therefore it's a 66.8% of admission rate to the hospital is explained by the two independent variables, the Wells index and availability of other health facilities in the catchment area. And therefore, the significant portion of the outcome variable is explained by these two independent variables. That's what we can see. Therefore, this is a combined effect of the two independent variables, and only the remaining portion of the dependent variable that's not explained is about approximately 33%, and something else explains that portion. So the model is fit. The model is fit. Now we move to the second to check another assumption, which is the assumption of absence of outliers. The data must be normally distributed. That is a requirement for multiple linear regression. And this can also be checked by looking at the standardized residuals. And the standardized residuals, the minimum and the maximum value of standardized residuals should fall between plus or minus 3, as we have discussed in the class. And therefore, in this particular example, if you use the minimum is minus 1.006 and the maximum is 1.167. Therefore, both fall within plus or minus 3. Therefore, we conclude that there is no outlier which can affect our final conclusion. Then the other one is the normality. The normality can be checked by several ways. One is to look at the PP plot, normal probability plot, where we look at how closer the scatters or the scattered dots plots are to the diagonal line, and the diagonal line is hypothetical line which represents this perfect normal distribution. And if the dots follow this diagonal line, we know that the data is approximately normally distributed. As you can see from this output, most of the points follow the diagonal line, and few of them are actually dispersed away. Therefore, because it is a visual impression, we can see that, of course, the data is approximately normally distributed, but we cannot be 100% sure. When we doubt our visual impressions, then we have to run a normality test, Kolmogorov-Smirnov test, or otherwise Shapiro-Wilk test. And as you can see, the table below the normal probability plot shows the Shapiro-Wilk test gives a p-value of 0.581, which is much greater than alpha of 0.05, and confirms that the data is perfectly normally distributed. Therefore, this is a concrete evidence we generate to be sure that the data is normally distributed. Therefore, as we have already seen, there is no outlier, the data is normally distributed, and the model is fit. Then the other one is we have to also check whether the relationship we are assessing is linear. That means if it is represented by a straight line. Otherwise, linear regression cannot be applicable in a situation when the relationship is not represented by a straight line. And therefore, to check this, we look at the scatter diagram of standardized residuals, and as you can see, the standardized residuals are not really well fitted to the straight line. As you can see, there are two clusters at the top of the diagram and below the diagram. This shows that this relationship is less likely to be represented by a straight line. Therefore, it's not a linear relationship. So this is a point of concern, and when this happens, then basically we have to be careful when we conclude our final output. The other one is also independence to claim or to confirm that the observation or data points are independent of one another. The dots must be approximately randomly distributed over the entire field. In this case, however, we don't see such random distribution, and we see some clustering of dots, and the clustering of dots indicates that dots that are clustering at one point are dependent or related to one another as compared to another cluster. Therefore, it seems that there is a violation of independence again. Another information we get from this is whether the variance is constant. Therefore, to check this, we have to, as we move from the left-hand side to the right side across the distribution, then the width of the distribution along the y-axis must be similar. And in that regard, we don't see much problem here, except we have one outlier dot which seems to violate. And if we have a concern with that, then we can actually avoid the outlier that we have, which violates the homoscedasticity of the distribution. Now, most of the assumptions are satisfied, and therefore now let us interpret the result. And the result can be interpreted first from table 3, the Anova table. As you know, Anova table is a family of multivariate analysis, and therefore it is one of the output we see when we run multiple linear regression. And the Anova table tells us the overall relationship between the independent variables and the dependent variable. And as you can see, F is 7.049 with a p-value of 0.021. So the Anova table tells us that there is an association between the two independent variables, which is availability of other health facilities and wealth index, and the dependent variable, which is admission rate to the hospital. So when Anova is significant, at this point we have to suspect or expect that at least one of the independent variable will be independent predictor of the outcome. That is the information that Anova provides. Now we move to the last one, which is a table of coefficients. That's where we get a concrete evidence regarding whether we have to reject an null hypothesis or not, and also where we identify the independent predictors of the outcome variable. As you can see, availability of other health facilities yields a beta value of 4 and the p-value of 0.007. So the availability of other health facilities in the catchment area is significant independent predictor of admission rate to the hospital with this p-value of as small as 0.007. And as you can see, beta is positive. This means then as number of other health facilities increase in the catchment area, then the number of patients admitted to the hospital also increase. That's what it tells us. So how does this happen then? Obviously it seems logical. And if there are several health facilities like health centers around, then it is likely that most of the patients with complicated cases are likely to be referred to the hospital, and therefore increases the probability of increasing the number of patients admitted. When you look at the second one, wealth index, the p-value is 0.081, as you can see. Despite the beta value is 2.8, it is not significant. Therefore, it is not significant predictor of hospital admission rate. This means the hospital provides the service with, I think, fair cost. Therefore, both wealthy people as well as poor people are equally likely to be admitted, and that's why wealth index does not really categorize, stratify people who are admitted to the hospital. The second one is obtaining the regression equation. Once you have reduced table of coefficients, then you can pick your beta naught, which is 13.449, and beta corresponding to first variable and beta corresponding to the second variable. And then you can, based on those information, you can construct your equation, which is y is equal to 13 plus 4.017 x1 plus 2.812 x2. That is the equation representing the model of admission to the hospital. The third one is 95% confidence interval has already been calculated for you. As you can see, for the first variable, it falls the 95% confidence interval for the beta value falls between 1.483 and 6.55. And as you can see, this confidence interval does not include 0, and therefore it is significant. That's why we reject the null hypothesis. For the second one, it includes 0. As you can see, the lower value for the beta is minus 448, and the upper one is 6.072, and therefore this do include 0 value, which does not include the null hypothesis. That's why we concluded that the wealth index is not predictor of admission rate. Okay, so now the second is about the effect of age, BMI, and annual income on fasting blood sugar. Therefore, this is you can get this data from data entitled Data for Exercise 50. You have this data with you, and you can run multiple linear regression to see the effect of this variable. In terms of research question, we can turn this to the research question, like what is the effect of age, BMI, and annual income In terms of research question, you can actually address this research question by doing this analysis. In terms of a research objective, you can put it like this, for example, to identify the effect of age, BMI, and annual income, okay, on fasting blood sugar, or to examine to what extent age, BMI, and annual income affects the fasting blood sugar, or does this affect the BMI of a respondent. Therefore, these are some of the research questions addressed by this. And so, in order to do this, you again follow the steps that have been indicated in your slide, the step 1 up to 5. So I have already indicated a space how you put each of the independent variables into the model and the dialog boxes. And once you have completed this, you will come up with this output. And the very first output, as we have already seen, is a model summary. The model summary provides R square of 0.356, which is 35.6% of the variance, and the fasting blood sugar is explained by the 3 independent variables. Therefore, the model is fit, and also the combined effect of the 3 variables on the fasting blood sugar amounts to 35.6%. Therefore, you can see that then there is a effect of these 3 variables on the outcome variable of our interest. Looking at the Anova table, shows again a significant test. Overall, there is association between the 3 independent variables, which is age, BMI, and annual income, on fasting blood sugar with a p-value of 0.00, and usually we don't write 00. This is recorded as 0.001, less than 0.001. Therefore, it is significant. So now we can expect that at least one of those 3 variables can independently predict the outcome. Then the next table is, as you can see, is a table of coefficients. In table of coefficient, we can see the individual effect of independent variables on the outcome by looking at their beta value, and also the combined effect has already been seen by looking at the R squared, which is at 5.6%. Now, from the 3 variables, age, annual income, and the BMI, you can see that age has a p-value of 0.013, which is very significant, and annual income has a p-value of 0.05. Therefore, these 2 independent variables are independent predictors of fasting blood sugar. And as you can see, the beta values are positive. This means as age increases, fasting blood sugar also increases. As annual income increases, fasting blood sugar also increases. And by what magnitude? That increases by the magnitude of the indicated beta value, as age increases by 1 year, or annual income increases by 1 unit. That it depends on how you measure the annual income, basically. BM doesn't have any relationship with fasting blood sugar based on this data. As you can see, the p-value is 0.497. This indicates that it does not predict, it doesn't have significant association with the fasting blood sugar. So you have to compare this with what is in the literature, and you have to justify why. If it is different, if it deviates from the literature, you have to actually discuss this, if this were your actual research. Okay. So our final conclusion is, therefore, age and annual income are independent predictor of fasting blood sugar, and the relationship is positive. I think the fulfillment of assumption exactly follows the same analogies, the same procedure that we have seen earlier. You look at the standardized residuals and see whether they fall within plus or minus 3 standard deviations. and then accordingly judge that the data is also normally distributed. As you can see, all the points fall on the diagonal line when you look at the normality, and also look at the standardized scatter diagram of standardized residuals. It's perfectly randomly distributed and also represented by a straight line, and has also a constant variance. Therefore, this shows a perfect fulfillment of assumptions required for multiple linear regression. Okay, the interpretations are very clearly and written in very detailed manner, and therefore look at them on read from your slide. The last point is logistic regression. Logistic regression